Well, friends, Mr. Burrell here. We're going to start talking about radical expressions. Okay, radical expressions, as a reminder, are expressions that have this symbol. This is called a radical symbol. Sometimes we call it a square root or a cube root if there's a little 3 here, or a 5th root or a 7th root, whatever. This is one of the kind of groups of types of expressions and functions that we're going to talk about. So in this lesson, we're going to specifically introduce these radical expressions and talk about operations with radical expressions, like addition, subtraction, multiplication, and division with radicals. Okay? So by the end of class today, we're going to start by reminding you how to change an exponential expression to radical form and vice versa. We're going to talk about simplifying a radical expression, and then we're going to talk about adding, subtracting, and multiplying and dividing radical expressions. Okay? So, first of all, let's go over some definitions. Some of these should be familiar. An exponent, remember, is a number that tells that the number of times a base is multiplied by itself. So if I have like 3 to the 4th power, this exponent tells me how many times am I multiplying 3, right? 3 to the 4th power is just 3 multiplied by itself 3 times. Okay, that's the general definition of what an exponent is. A radical, as a reminder, is this square root symbol. I say square root lightly because without an index that we'll talk about in just a second, we call it a square root. But a radical can have a variety of indexes or indices. An index is the number outside the radical that tells me what type of root I'm dealing with. So this is a square root, or I could put a little 2 there to denote a square root. But I could have a cube root, again, a 6th root. I could have a 100th root. That just tells me what type of radical I am talking about, what type of root I'm looking at. And note that the radicand, that's a word maybe we don't toss around as much, but a radicand is the expression that's inside or underneath the radical symbol, okay? So whatever's under here, say this is like 4x squared, that is the radicand, whatever I'm taking the root of, okay? So when I'm simplifying radical expressions, the radical symbol, index, and radicand almost kind of act as a variable, okay? Similar to the fact that only like terms can actually be combined together when I'm adding or subtracting, okay? So for example, if I add 2x plus 3x, I can add those together because they're like terms. 2x's plus 3x's is 5x's. In a similar fashion, if I add 2 square root of 5 plus 3 square root of 5, I have 2 of this thing and 3 of this thing. They're the same thing. If I add them together, I'm going to get 5 of those, so 5 square root of 5. But similar to the fact, if I had like 2x plus 3y, I can't simplify that anymore. I can't combine those together. So if I had 2 square root of 5 plus 3 square root of 7, I can't add those together because they are not the same. They are not like terms, okay? So as far as addition and subtraction go, those operations dealing with radicals behave very similar to how I would do operations with polynomial functions, okay? Before we get too far into that, let's remind you, you've done this already, but let's practice rewriting exponential expressions with fraction exponents as radical expressions and vice versa. So right here I have 5x to the 1/2 power. Remember when I have a fraction exponent, I can rewrite this as a radical, where this bottom number becomes the index for the root, and then this top number becomes the power that this is raised to. So really 5x to the 1/2 power is the same as the square root of 5x to the 1 power. Or to the 1 power isn't going to change anything. So really I could think of this as just the square root of 5x. Okay? 4n to the 2/3 power could be written as the cube root of 4n squared. Okay? Or note that this is going to be the same thing as the cube root of 4n squared. Okay? It doesn't matter where that exponent goes, on the inside or outside of the radical. Either one is going to be fine. Vice versa, the cube root of 4x is going to be rewritten as 4x to the 3's in the bottom. And since this isn't raised to a power, I can envision that it's raised to the 1 power. So that's going to be the same as 4x to the 1/3. The square root of 3t cubed is going to be 3t to the 3/2 power, because this is a square root. So that's the number that's going to be in the bottom. It's raised to the 3rd power. That's going to go on the top. That's a quick review because you've learned that already. But that's how I write expressions in radical form versus exponential form and how I relate between the two. Okay? So let's practice simplifying some expressions. Okay? So first of all, here I just have 2 times the square root of 48. I'm not doing any adding or subtracting or anything like that. I'm just simplifying this radical, which again you have done before. So let's just review briefly. In order to simplify the square root of 48, I'm going to go ahead and create a little factor tree to find all the factors of 48. 48 is, let's see, 6 times 8. 6 is 2 times 3. 8 is 2 times 4. And 4 is 2 times 2. And if you've had me in class before, you know that I like to use what I call the number prison analogy. So here are all the factors of 48 broken down into their prime factors. So I have 2 times 2 times 2 times 2 times 3. And in order to escape from this radical prison, it's a pretty radical prison. In order to escape, you have to escape in pairs. So I have a pair of 2s and a pair of 2s right here. But in escaping, one in each partnership is going to die, get caught in the electric fence or something. So this 2 and this 2 go away. But each of these 2s escape from number prison. So this 2 has already escaped. There's 2 more 2s that escape from number prison. And left inside the prison is this 3. So I end up with 2 times 2 times 2, which is 8 times the square root of 3. So 2 times the square root of 48 and 8 times the square root of 3 are equivalent expressions. This is just simplified. Okay? So in a similar fashion, on example number 6, the cube root of 81, let's break down 81. 81 is 9 times 9. Each of those 9s are 3 times 3. This is a cube root. So the cube root number prison is a little bit more radical. It's a little bit tighter security. In order to escape from cube root number prison, you have to escape in 3s. And still only one is going to survive. Those 2, 3 get caught in the moat or eaten by alligators. Okay? So on the outside of this prison, I have -4 times this 3 that escaped. And on the inside of this prison, I have this lonely 3 that didn't have a trio to escape with. So I'm left with -12 times the square root of 3. Okay? So again, -12 times the, cube root of 3 and -4 times the cube root of 81 are equivalent expressions. This one is just simplified. Okay? Most of that should be reviewed. Now let's talk about some operations with these radical expressions. So here I have -2 square root of 18 minus 2 square root of 2 plus 3 square root of 18. Okay, remember, when I'm adding or subtracting radical expressions, I can only combine them together if I have the same radical, the same radicand. So like these 2 I could combine together, but this one I cannot. Let's combine those together for kicks and giggles right now. -2 square root of 18 plus 3 square root of 18 is going to be 1 square root of 18. So I have 1 square root of 18 minus 2 square root of 2. Okay? Now I might be thinking to myself, I can't simplify this anymore. But note that the square root of 18 on its own can be simplified a little bit more. 18 is 9 times 2. 9 is 3 times 3. I have a pair of 3s that can escape from this prison. One will get caught in the electric fence or something. So this 3 escapes, leaving me with this lonely 2 in prison. So I have 3 square root of 2 minus 2 square root of 2. Now I have like terms again. I have the same radicand underneath each of these square roots. So 3 square root of 2 minus 2 square root of 2 is going to be 1 square root of 2, or just square root of 2. That is my final simplified answer. -2 square root of 18 minus 2 square root of 2 plus 3 square root of 18 all simplifies down to the square root of 2. Okay? Let's look at example number 8. Similar thing. I have 2 square root of 54 minus the square root of 54. I could combine those together right now to just be 1 square root of 54 plus 2 square root of 24. So now I want to simplify each of these radical expressions to see if they simplify to a radicand where I can combine them together. So let's see, 54 is 9 times 6. 9 is 3 times 3. 6 is 2 times 3. I have a pair of 3s that can escape. 1 will not make it. So I end up with 3 times the square root of 2 times 3 gives me 6. So I have 3 times the square root of 6. 24 is 6 times 4. 6 is 3 times 2. 4 is 2 times 2. I have a pair of 2s that can escape. 1 will not make it. So I have a 2 that escapes, and then 3 times 2 is still left on the underside, so I'm left with the square root of 6 underneath that square root. Notice now I can combine those together. 3 square root of 6 plus 2 square root of 6 is 5 square root of 6. So that's my final answer there. That's how I deal with adding and subtracting radicals together. I can combine radicals together if they have the same radicand. All right, let's talk about some multiplication. So in example number 9, I have negative 2 square root of 3 times parentheses 5 minus 4 square root of 3. Okay. Well, I'm going to go ahead and multiply these two expressions similarly to how I would when I'm distributing terms in like a polynomial expression. So I need to multiply negative 2 square root of 3 by both of these terms on the inside. So let's do negative 2 times the square root of 3, or negative 2 square root of 3 times 5. Okay? Well, when I do negative 2 square root of 3 times 5, notice that 5 doesn't have a radical attached to it, so this 5 is going to be multiplied by the negative 2. Kind of like if I had negative 2x times 5, the 5 is a constant number, so it's just going to be multiplied by the other constant number, that coefficient. So negative 2 square root of 3 times 5 is going to be negative 10 square root of 3, okay? But now negative 2 square root of 3 times negative 4 square root of 3, that's going to be a little bit different. I'm going to multiply the negative 2 and the negative 4 together, which is going to give me a positive 8. Now I'm going to multiply the square root of 3 and the square root of 3 together, okay? The square root of radicals, when I multiply them together, they will stay underneath the radical, but the numbers on the inside are going to multiply together. So the square root of 3 times the square root of 3 is going to be this square root of 9. When I'm multiplying radicals, the radicands do not need to be the same. In this case they are, but they do not need to be the same. Okay? So I have negative 10 square root of 3 plus 8 square root of 9. But you'll probably notice I can simplify this a little bit more, because the square root of 9, hopefully you know that off the bat, is just equal to 3. So really this is negative 10 square root of 3 plus 8 times 3, which is negative 10 square root of 3 plus 24. So that is my final simplified answer after multiplying those expressions together. Negative 10 square root of 3 plus 24. Let's do another multiplication example so we can get some more practice. In example number 10, I have 5 plus the square root of 3 times negative 3 plus 4 times the square root of 3. So I'm going to have to distribute, in this problem, 5 times negative 3, 5 times 4 square root of 3, and then square root of 3 times negative 3, and the square root of 3 times 4 square root of 3. Okay? So 5 times negative 3, that's negative 15. 5 times 4 square root of 3, that's going to give me 20 square root of 3, because the 5 and the 4 will multiply together. Square root of 3 times negative 3 is just going to be negative 3 times the square root of 3. And then the square root of 3 times 4 square root of 3 is going to be 4 times the square root of 9, which we determined was going to be 3. Okay, so 4 times 3, it's going to be 12. Now let's combine some like terms. Negative 15 and 12 combine to make negative 3. And coming back to our addition and subtraction talk, 20 square root of 3 minus 3 square root of 3 is going to be 17 square root of 3. So my final answer there is negative 3 plus 17 square root of 3. Okay? That's how I deal with multiplying expressions together that have radicals in them. Okay? So we talked about addition, we've talked about subtraction, we've talked about multiplication. Let's talk about some division. Okay? Example number 11. I have 3 square root of 15 over 2 square root of 12. So there's a couple things I could do here. First of all, when I'm looking at my coefficients and my radicands, if right from the beginning the coefficients can be simplified, like if 3 over 2 could be written as a simpler fraction, I could do that right from the get-go. Or if the radicands, 15 over 12, could be simplified, I could simplify those right from the get-go. Okay, so let's do it that way, and I'll show you another way you could go about simplifying this problem. The square root of 15 over the square root of 12, 15 over 12 can reduce because the top and the bottom are both divisible by 3, right? So if I divide by 3 on the top and bottom, I'm going to end up with 5 over 4. So really I could rewrite this as 3 square root of 5 over 2 square root of 4, okay? So now let's determine if I can simplify this any farther. Well, the square root of 5 isn't going to simplify any farther, but the square root of 4 is. The square root of 4 is 2. So this is going to be 3 square root of 5 over 2 times 2, which gives me a final answer of 3 square root of 5 over 4. Okay, that's my final answer. Another way that I could go about dividing and simplifying these two expressions is I could simplify the top and the bottom separately. So the square root of 15, if I create a little factor tree for 15, that's 5 times 3. That square root is not going to simplify. If I try to simplify the square root of 12, 12 is 4 times 3. 4 is 2 times 2. And alas, I have a 2 that can escape from prison. Okay, so I end up with out in front, I have 2 times this 2 that's escaping, which is 4, times the square root of this 3 that was left on the inside. Okay, so now I have 3 square root of 15 over 4 square root of 3. Now let's see if I can simplify either the coefficients or the radicands. Well, 3 over 4 can't simplify. But 15 over 3 can simplify to just be 5 over 1. So I end up with the square root of 5 on the top and the square root of 1 on the bottom, but the square root of 1 is just 1. So I end up with 3 square root of 5 over 4, which is the same thing I got the other way. So you have some liberties when I'm simplifying radical expressions, but the key to remember is I can simplify terms that are underneath the square root together. So 15, the square root of 15 over 12 really is the same thing as the square root of 15 over 12. And I can treat that as one fraction, and I can simplify it and then simplify the respective square roots. Okay. The last one I want to look at is example number 12. This says 2 over 5 minus 4 square root of 2. So this is kind of potentially already simplified, but something that potentially shows up on the ACT kind of often, or something that mathematicians like to do, is something called rationalizing the denominator. So you'll notice in the denominator, I have a square root here. Mathematicians don't like that. They don't like irrational expressions in the denominator of a fraction. So I'm going to do something called rationalizing the denominator. So follow along with me here just for a moment. In the bottom here is 5 minus 4 times the square root of 2. What I'm going to do is I'm going to multiply the top and bottom of this fraction by 5 plus 4 times the square root of 2. 5 plus 4 times the square root of 2. I'm going to multiply by that on the top and on the bottom. Whoops, here we go. Sometimes this expression is called the conjugate. So when I multiply by the same thing that's in the denominator here, but I switch this sign, it's called the conjugate. You might be asking, Mr. Brill, why am I multiplying by that? Watch. Okay, just bear with me for a moment. So if I multiply the top here, 2 times 5 is 10. 2 times 4 square root of 2 is 8 square root of 2. And then the bottom I'm going to have to distribute. So 5 times 5 is 25. 5 times 4 square root of 2 is 20 square root of 2. Negative 4 square root of 2 times 5 is negative 20 square root of 2. And then negative 4 square root of 2 times positive 4 square root of 2 is going to be negative 16 square root of 4. Okay? Let's simplify this a little bit. So I have 10 plus 8 square root of 2 in the top. In the bottom, I have 25, and then 20 square root of 2 minus 20 square root of 2. Notice that those are just going to cancel out. They're going to go away. And then minus 16 times the square root of 4 is going to be minus 16 times 2, which is minus 32. Okay? Which I could then simplify to 10 plus 8 square root of 2 over 25 minus 32 is negative 7. So note, when I multiplied by the conjugate, all the terms with radicals in them went away. So I have rationalized the denominator. There are no more radicals, there are no more square roots or cube roots or whatever in the bottom of this fraction. This would be my result, my answer, if I asked you to rationalize the denominator. Might seem like maybe a little bit pointless, and maybe it is a little bit pointless, but something that mathematicians like to do that sometimes presents itself on tests like the ACT or whatever to rationalize the denominator. So there you go. That's all I have here. Hopefully you feel comfortable simplifying a radical expression, changing expressions from exponential to radical form and vice versa. And then hopefully you can add, subtract, multiply, and divide radical expressions. So I hope that was helpful. Please let me know if you have any questions, and I hope you had as much fun as I did.